So, we all thought the hard part was getting there. The 8.5-minute launch atop the Space Launch System, that skyscraper of fire and controlled explosion climbing out of Florida, the 600,000-mile journey around the Moon, through the Van Allen radiation belts, past the point where Earth hangs in the rearview mirror as a fragile blue marble, the 6 days in deep space where solar particle events could fry your central nervous system with no hospital for 240,000 miles. That's what NASA calls the impossible part. That's what the press releases focus on, the grandeur of leaving Earth. But as Artemis II gets closer to launch and that November 2025 window approaches, though insiders whisper it's already slipping to 2026, engineers at Johnson Space Center are realizing the math is backwards, the physics is backwards, because we just got hit with a brutal update that didn't make the evening news, buried in technical reports with boring titles like Post-Flight Analysis of Thermal Protection System Performance. The update is this: leaving the Moon was easy, coming home is the trap. And the re-entry physics just revealed why those final 8 minutes might be unsurvivable, even if everything else goes perfectly, even if the launch is flawless, even if the lunar flyby is picture perfect, even if the crew is healthy and the systems are green. The 8 minutes of terror, that's what we should be calling it, not the launch, are the most dangerous phase of the entire mission. And unlike the launch, where mission control can abort, where the crew has ejection seats and escape towers and options, these 8 minutes have no escape hatch. No do-overs, no mission control magic, just fire, force, and the merciless laws of atmospheric entry. First, the numbers from the Artemis I mission. To return from the Moon, you need to hit Earth's atmosphere at exactly 25,000 miles per hour, Mach 32. Fast enough to cross the continental United States in 10 minutes. Now that sounds manageable, right? Apollo did it 9 times between 1968 and 1972, 50 years ago, with computers less powerful than a modern calculator. The physics haven't changed. Gravity hasn't changed. The atmosphere is still the same thickness. But Artemis the seat is violating the one safety rule NASA thought they mastered: predictability. During Artemis I, the uncrewed test flight in December 2022, the Avcoat heat shield didn't behave. It didn't ablate evenly. Some areas experienced 50% more heating than the computer models predicted. The charring was asymmetric. The thermal protection worked. The capsule survived, but it worked too hard. It sacrificed material in ways that suggested the mathematical models were missing something fundamental about how Orion interacts with hypersonic plasma. The capsule came back empty. No crew to worry about, no heartbeats to monitor, no families watching the live feed. But now we're sending 4 humans, Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, on the first crewed flight of a vehicle that already showed us the math was wrong in an uncrewed test. The heat shield worked, but it worked too hard. And on Artemis II, there are no second chances. If that uneven heating repeats in a more extreme portion of the entry corridor, if the skip re-entry creates thermal gradients the material can't handle, the shield could crack, delaminate, fail. This is called the skip re-entry maneuver, and it's the most dangerous gamble in human spaceflight. Here's how it works. Instead of one brutal, continuous plunge through the atmosphere like Apollo used, Orion will hit the atmosphere at a shallow angle, use the lift generated by its blunt body shape to literally skip back up to 100,000 feet, like a stone skimming across a lake, then dive again for the final descent. Think about that. You're hitting a wall of air at Mach 32, bouncing off it, then hitting it again, just like a Ponzi scheme collapses under its own weight when too many layers are added. The skip re-entry adds complexity that collapses the safety margins. Every skip introduces variables: angle of attack, velocity decay, thermal accumulation. To launch a crew home safely requires not just surviving one entry, but 2. First entry, the skip, then second entry. That's double jeopardy. The heat that soaked into the Avcoat during that first dip doesn't magically disappear during the skip upward. Like a steak that keeps cooking inside after you take it off the grill, the exterior might cool slightly in the thin upper atmosphere, but the interior stress, the thermal gradients, the structural fatigue, they're still building. The delayed heating would be cracking open the thermal protection in ways the Apollo astronauts never faced because they used direct entry. One and done. But Orion can't do direct entry. It's too heavy, too complex. The service module, built by the European Space Agency, adds mass. The modern avionics add mass. The life support for 4 crew for 21 days adds mass. Apollo carried 3 men for 14 days. Orion carries 4 for 21. That extra weight means Orion comes in hotter, heavier, and harder than any Apollo capsule ever did. So NASA needs the skip to bleed off velocity gradually enough to hit the precise Pacific landing zone where recovery ships wait. Without the skip, the landing footprint is thousands of miles long. With the skip, it's precise, but precarious. Here's the trap. On Earth, we have tested direct entry thousands of times. Mercury, Gemini, Apollo, Soyuz, Dragon. We know direct entry. We have heritage. But a skip re-entry with a crewed vehicle? The heritage is thin. The X-15 did skips. The Apollo Command Module was capable of it but never used it operationally. The Zond missions flew skips, but they were uncrewed or carried animals. No human being has ever experienced a skip re-entry from lunar return velocity. Not once. Not ever. So the theory is that the outer crust of our understanding, our computer models, our wind tunnel tests, our arc jet simulations, had their safety margins altered by the Artemis I flight data. The uneven heating suggests the plasma sheath interacts with Orion's specific geometry in ways we didn't predict. Laboratory experiments on Earth can simulate pieces of re-entry, but they can't simulate the full 5,000-degree plasma envelope for 8 continuous minutes. They can't simulate the skip, so when Artemis II hits that atmosphere and gets blasted with superheated air turned into an electrified soup of dissociated atoms, the outer assumption either holds or fails like an eggshell cracking. And now we're seeing deeper material, the actual flight physics that was protected from theory by the limited data of Artemis I. And that deeper reality has normal risk chemistry just like Apollo, but with modern complexity that behaves like a completely different vehicle. But here's another weird thing. NASA's answer to the communication problem during this phase is called the plasma blackout. It sounds like a technical inconvenience, but the new data from Artemis I reveals something shocking. The blackout lasted longer than predicted, and the electromagnetic interference with Orion's modern avionics was stronger than models suggested. To maintain orientation during the skip, you need thrusters firing precisely. When the plasma sheath surrounds the capsule, it blocks radio signals. But it also creates a Faraday cage effect that can induce currents in the spacecraft's wiring. Finding a way to steer through the skip without reliable comms and with potential electrical anomalies is like finding ocean water with no salt. It violates the assumptions of control. The blackout lasts 3 to 4 minutes. 3 to 4 minutes where Houston hears nothing but static. 3 to 4 minutes where Reid Wiseman can't call for help if the capsule starts tumbling, if the heat shield crack propagates, if the G-forces spike. The crew is alone. Truly alone. For context, the Apollo 13 crew faced a re-entry blackout where engineers weren't sure the heat shield had survived the cold of space. They held their breath for 3 minutes. That was with a simple vehicle and direct entry. Orion is more complex, more automated, more dependent on systems that can't be monitored during the silence. So where does the control come from? Well, I think the reason for this is something called the autonomous guidance limit. Let me explain what that actually means. Because despite the name, it's not just autopilot. It's a pre-programmed sequence of thruster firings based on inertial measurement units, gyros, and accelerometers that assume the capsule is behaving within predicted parameters. But if the skip doesn't go exactly as planned, if the atmospheric density is slightly different, if the capsule's center of gravity shifts due to crew movement or fluid sloshing, the autonomous system might make the wrong correction. It might fire the thrusters too hard, not hard enough, or in the wrong direction. And with the plasma blocking both radio signals and star trackers, the capsule is flying blind. Just like a driver in whiteout conditions who can't see the road and can't hear GPS, the system is guessing based on last known position. I ran the numbers. If the capsule enters just 0.5 degrees too steep during the first dip, the skip won't happen. Instead of bouncing, it'll dig in. The G-forces don't just increase, they spike exponentially, from the planned 8 Gs to potentially 15 Gs or higher. At 8 Gs, a 180-pound astronaut weighs 1,440 pounds. Breathing becomes a conscious effort, short grunting exhales against the force. Vision tunnels, blood drains from the brain. At 15 Gs, consciousness is lost in seconds. The heart can't pump blood against that pressure. The lungs collapse under their own weight. The chest wall can't expand. You suffocate while fully conscious, unable to draw breath, crushed by physics itself. And here's the crazy part. During centrifuge training, the Artemis crew practiced for 8 Gs. They know what it feels like, an elephant sitting on their chest. But if the skip fails and they hit 12 or 15 Gs, that training is irrelevant. Nobody trains for 15 Gs because 15 Gs is considered unsurvivable for the duration of a re-entry. It's not a spike, it's a sustained pressure lasting minutes. The math says that if the entry angle is wrong by that half degree, the crew arrives at the splashdown site unconscious or dead, regardless of what the heat shield does. SpaceX published Dragon re-entry data before NASA released the detailed Artemis I heat shield analysis. The data shows the exact same gap. Direct entry is manageable, skip entry is volatile. The comparison to the Soyuz disasters is inevitable. In 1967, Vladimir Komarov died when his parachutes failed. In 1971, the Soyuz 11 crew asphyxiated during re-entry when a valve opened prematurely. These weren't design failures, they were integration failures, systems that worked in testing but failed in the real flight environment. Artemis II faces similar unknowns, but with a maneuver, skip re-entry, that has no human heritage at all. But wait, there's something even stranger happening that nobody's talking about at the press conferences. The parachute system. Everyone assumes that if the heat shield holds and the skip works, the parachutes are the safe part, the easy part. The grand finale where the capsule descends gently into the Pacific while the crew waves to the recovery divers. But new data reveals that Artemis II is still showing a parachute problem as it's getting closer to launch. As you probably know, Orion has 11 parachutes, a complex ballet of drogue chutes, pilot chutes, and 3 massive mains spanning almost 100 feet. We've been testing this system for years. But here's the crazy part. In 2019, a drop test saw only 2 of 3 main parachutes deploy correctly. The capsule still landed safely in that test because it was uncrewed and the remaining 2 chutes were sufficient for the test weight. But with 4 crew members instead of a dummy, the margin vanishes. You need all 3. I did the math and calculated exactly where the risk accumulates. If the drogue chutes experience what's called drogue skip, where the capsule is swinging too violently when they deploy, the drogues can tangle or fail to stabilize the vehicle. Then, at 9,000 feet, when the mains deploy automatically based on barometric pressure, they deploy into chaos. Lines can cross, chutes can collide, 2 chutes become 1 or 0. Here's the trap. The capsule has to slow from 300 miles per hour to 20 miles per hour before hitting the ocean. That's a massive energy bleed in a short time. If the parachutes deploy late, by even seconds, because of a barometric sensor error or a software glitch, the impact velocity doubles. Apollo astronauts describe splashdown at 20 mAh as hitting a brick wall. Now imagine hitting that wall at 40 mAh. The capsule could flip, the heat shield could separate, the crew module could flood, or the impact could simply break bones, cause internal injuries, or trigger a structural failure that releases toxic propellant fumes into the cabin. And the kicker? There's no backup, no ejection seats during re-entry, no launch escape tower, just the capsule, the chutes, and the ocean. If the chutes fail, the crew rides a 10-ton metal cone to terminal velocity impact. The crater would be 6 feet deep, just like Komarov's. If the parachute problem is real, then the psychology collapses too. High SEAL studies, the Mars isolation research, showed crews break down after 8 months of confinement. But Artemis II isn't about long-term isolation, it's about acute stress concentration. The crew knows that for 8 minutes they are helpless. They know about the heat shield anomaly from Artemis I. They know about the skip maneuver that no human has ever survived. They know about the blackout where they can't call for help. They know about the G-forces that could crush them unconscious. They know about the parachutes that might tangle. Victor Glover, the pilot, will be monitoring the trajectory. Christina Koch will be watching the systems. Jeremy Hansen will be handling communications until the static hits. Reid Wiseman, the commander, will have his hands on the abort handles, even though he knows there's no abort during re-entry. For 8 minutes, 4 humans will sit in that cone, surrounded by fire, crushed by force, deafened by static, swinging beneath parachutes that might not open, knowing that 200,000 people applied for Mars 1, knowing it was suicide, but they applied for Artemis thinking someone had solved the return trip. The sunk cost fallacy is the killer here too. Once that service module separates and the crew commits to entry, there's no turning back. They can't radio for rescue. There is no cavalry. So if the heat shield shows cracks on the internal cameras, if the G-meter spikes past 10, if the capsule starts tumbling, they just have to ride it out. Better to die trying to come home than admit you're trapped in a metal tomb falling from the sky. But here's where it gets darker. The Artemis program isn't supposed to end with Artemis II. This is supposed to be the gateway. Artemis III will land on the moon. Artemis IV will build the gateway station, eventually Mars. But every single one of those missions faces these same 8 minutes. Every return from deep space requires surviving the plasma, the skip, the blackout, the G-forces, the chutes. If Orion fails, if Artemis II teaches us that the skip re-entry is too dangerous, that the heat shield is unreliable, that the margins are too thin, then the entire lunar program collapses, the Mars timeline evaporates. We'd be trapped in low Earth orbit forever, too afraid to reach again for the moon, not because we can't get there, but because we can't get back. The 8 minutes become the gatekeeper to the solar system. Survive them, and humanity is multiplanetary. Fail, and we're grounded. The Apollo program had heritage. By Apollo 11, the heat shield was proven. The entry profile was proven. The parachutes were proven. Artemis II is Apollo 8 all over again, the first crewed flight to the moon, but with a vehicle that's heavier, more complex, and using an entry profile that no astronaut has ever tested. The simulations aren't reality. The Artemis I heat shield proved that. The 2019 parachute test proved that. So when you watch that launch, when you see the SLS rocket climb into the Florida sky on that November morning, remember that the mission isn't over when they leave the moon. The most dangerous part is still to come. 8 minutes. That's all it takes to go from the edge of space to the surface of the ocean. 8 minutes of fire and force and silence. 8 minutes where 4 humans will be closer to death than most of us will ever be, yet also demonstrating what humanity can achieve when we refuse to accept limits. The heat shield will glow at 5,000 degrees, half as hot as the surface of the sun. The plasma will build. The G-forces will crush at 8 Gs, maybe more. The blackout will descend for 3 minutes of silence. The skip will either work or it won't. the parachutes will either bloom or tangle. And then, if everything works, if the math holds, if the physics agrees to let them pass, the recovery divers will confirm 4 humans survived the most terrifying 8 minutes in spaceflight history. But until that confirmation comes, until the hatch swings open and we see those faces, until then, those 8 minutes will be the longest in human history. Because in those 8 minutes, there's no mission control, no help, no second chances. Just 4 humans, a capsule, and the violent physics of coming home. 8 minutes to live. Let's hope that's enough. So, if you watched to the end, tell me, knowing the heat shield already failed the prediction test, would you still strap in for the skip? Drop your theories below. Also, smash that like and subscribe, and have a blessed day.